All right, so our next speaker is Yujia Peng, postdoc. I'm pretty sure I messed up again your name. I'm sorry.
It's fine.
Yujia Peng,
Yujia, yeah.
postdoc. Yujia, right. It's so difficult to change your biases. Okay, so Yujia is a postdoc at UCLA, and she's working in the lab of Dr. Krasky, and she's going, well, feel free to share your screen. So she's going to present her recent work on threat neurocircuitry predicts the development of anxiety and depression symptoms in a longitudinal study. And interestingly enough, this is joint work with the next speaker as well. So we're going to be like talking about this for quite a while, I guess. But in the so in the free time, like she likes to play with her cat, and I want to know the name of the cat first. Second, to learn piano and play also Dungeons and Dragons. So what's the name of the cat before giving the stage to you?
She's called Potato.
Oh, wow. Amazing. All right. So with no further ado, go ahead.
Thank you very much for the introduction, and thank you everyone for being here. It's my great pleasure to talk about our recent ongoing study. It's a collaboration between UCLA and Northwestern University. So let's jump right in. Anxiety disorders are associated with a heightened tendency to acquire maladaptive fears and a reduced capacity to extinguish them, and therefore maladaptive fear learning is considered a central mechanism behind the development and treatment of anxiety disorders. Anxiety is also linked to impaired threat processing and dysregulated activity of threat neurocircuitry. For example, heightened reactivity to threatening cues in amygdala, dorsal ACC, and insula, impaired safety signaling in VMPFC, and impaired memory encoding in hippocampus. However, the disrupted functioning of threat neurocircuitries may not be specific to anxiety disorders, and in particular, abnormal processing in same circuits was also implicated in depression. This may not be surprising given the high comorbidity of anxiety and depression, but it's also possible that the symptoms that are unique to anxiety and depression map onto different disrupted functioning of threat neurocircuitries. So dimensional symptom models allow us to examine how threat neurocircuitry relate to symptom factors that are shared versus unique to anxiety and depression. A tri-level model with 3 hierarchical levels was previously established. On top, we have a broad factor, general distress, which indicate the negative effect that's common to anxiety and depression. On the second layer, the intermediate factors, there are 2 components. One is fear, which is more specific to anxiety disorders, and anhedonic apprehension, which is more specific to depression. On the bottom layer, there are narrow symptom dimensions that map onto anxiety and depression, respectively. In the current study, we hope to investigate how longitudinal changes of symptom dimensions map onto anxiety and depression, especially the threat neurocircuitry. We'll in particularly focus on the transition from adolescence to adulthood, which is marked by higher life stress and a higher risk of psychopathology. We collected symptom measures at 4 different time points from baseline and to 36 months. The symptom dimensions were estimated through a tri-level factorial model for each time point, and linear slopes were extracted for the change of symptom dimensions over the 4 time points. Additionally, we collected fMRI scans at baseline and 36 months. During this, participants finished a Pavlovian fear conditioning task with 3 phases: fear acquisition, extinction, and extinction recall. Specifically, on each trial, participants will see a context image for 3 seconds, followed by an image with conditional stimulus. For those conditional stimulus associated with shock, we call them CS+. For those not associated with shock, we call them CS-. During extinction learning, some of the CS+ stimuli went through extinction learning, and we call them CS+E. For those CS+ never went through extinction, we call them CS+U. So for fear acquisition, we specifically focus on the contrast between CS+ and CS-, indicating the process of fear acquisition. For fear extinction, we focus on early CS+E versus late CS+E, indicating the process of the extinction of fear. And for extinction recall, we focus on early CS+E versus early CS+U, indicating the retention of the safety signal. We focus on 7 ROIs from the threat neurocircuitry given by previous evidence from humans and animals. And we implemented 2 linear mixed models for each one of the 3 fear conditioning stages. In model 1, we focus on the baseline threat neuroreactivity. And in model 2, we focus on the neuroreactivity change over the 3 years, meaning using 36 months subtracting baseline. The predictors are the same. We included tri-level symptom slopes for general distress, fear, and anhedonia. ROI indices were entered as repeated measures, and we include 3 covariates. We have 2 major findings. For finding 1, we found that neurothreat reactivity during fear acquisition at baseline is positively associated with changes in fear symptoms over time. So in other words, if a person has greater neuroreactivity to fearful stimuli at baseline, this person is more likely to show a greater increase in fear symptoms during the 3-year prospective period. This may suggest that if a person is more sensitive to the fearful information in the environment, they may be more likely to express more fear-related symptoms from adolescence to adulthood. We also further break down the effect to see the pattern of individual ROIs, and we found 2 groups of ROIs, one group showing positive correlations between fear acquisition contrast and fear slopes. They are amygdala, hippocampus, anterior insula, and also BNST. Another group showed negative correlations, especially VMPFC. This may indicate different roles of ROIs from the threat neurocircuitry in this fear acquisition process. One group may show heightened reactivity to fear acquisition for those individuals with higher increase of fear symptoms, whereas the second group may show a reduced top-down regulation for those individuals with greater increase of fear symptoms. Our second finding was that changes of neurothreat reactivity during fear extinction recall is negatively associated with the changes of general distress symptoms over time. Let's unpack this effect a little bit. So when we separate the effect from T4, the 36-month, and baseline T1, we found that the effect was mainly driven by T4 at 36 months, meaning that a greater increase in general distress over the 3 years are associated with deficits in retrieving safety memory at 36 months. In other words, if a person expressed more negative affect during the 3 years from adolescence to adulthood, this person may be more likely to show a worse performance in retrieving the safety signal after the 3 years. We also examined the individual patterns of ROIs, but we did not find a very clear story, and in the future, we'll need to further examine the individual roles of ROIs in this threat neurocircuitry regarding safety signal retention. So together, we found greater neuroreactivity to fearful stimuli at baseline is associated with a greater increase in fearful symptoms during the 3-year prospective period. We also found greater increases in general distress over 3 years are associated with deficits in retrieving safety memory at 36 months. Together, the findings show a promise of fMRI fear conditioning paradigm as a tool for classifying individuals into empirically established symptom profiles. I want to thank all the collaborators who made this study possible, and thank you for your attention.
Thank you very much. Great talk. So again, like while people ask questions or type the questions, please do use the Q&A button at the bottom of Zoom. I have a question on your first finding. If you can go back to that slide. Because to me, I mean, I was wondering whether you have taken into account all the possible confounding factors here, because the slope, of course, is not, I mean, it is significant, but not extremely significant, I would say. So I was wondering if you had computed the p-value using any sort of statistical correction for multiple comparisons, or whether how you corrected for age and gender and this type of compounding.
Yeah, thank you for the question. It's a very fair one. So we included age, race, and gender as covariates, and we modeled one linear mixed model for the all three symptom dimensions. So we want to reduce the number of models as much as possible, but we also realize it's a relatively small effect. This may be due to the reason that our population is also from a typical developing population, not a clinical population. We tried to include a large variety of sensitivity to reward and threat, but in the end, the data may show a very clustered normal distribution instead of a more extreme distribution.
I see. And are you planning to further validate this with larger population, or maybe also using clinical population?
Yeah, that would be a very good idea.
Okay. Yeah. Jesse, we can't hear you, but I know you have a question. Okay, now yes.
Hear me now?
Yeah.
I was just wondering if maybe you're in the same case as I was. I was kind of coming in on a project that was already going, but if not, I was wondering what kind of got you interested, or how like this project study came about. If you were following up on like a previous interest or finding.
We are kind of in the same situation as Jesse. We came in to this very big project that's already going on. But I think the basic idea behind this project is to find the relation between the neural activity and other dimensions following an RDoC approach. We hope to find relations between like physiological data, behavioral data, self-report symptoms, and neural activity to both threat and reward. We hope to like figure out a big picture of how we can map the symptoms onto different domains.
That's very interesting. Yes, that's exactly what I was wondering, was kind of how this fits into a big picture of what you guys might be working on.
Right.
So what are the next steps?
So first, we will need to figure out the individual relations of ROIs, how they map onto the threat processing. And in the future, we will also expand this threat fear conditioning task into reward-related tasks, and also see what the roles of physiological data and behavioral data are in this process. So it's a very huge project. Right now, we are just looking at one small piece of it. And also, we are right now using a univariate analysis approach. And in the future, we hope to see a multivariate analysis and also connectivity analysis.
Right. Yeah. In fact, that was my next question. If you were planning to do any connectivity analysis on this.
Yeah, that will be.
Did you already like record like other behavioral data with this experiment here that you could like?
Right. We have a few behavioral tasks like approach, no approach task, but we haven't looked into the details.
Okay.
Seems very exciting.
Thank you.
Yeah, in terms of next steps, also, Yujia, I don't know if you want to talk at all about this, but the PIs on this study, as soon as COVID hit, kind of jumped on the opportunity to contact a bunch of the participants and see if they would fill out questionnaire data again. And the sneak peek is that, like, as you might guess, we're seeing like increases in anxiety and depression measures.
Okay.
So it's kind of a unique longitudinal data set that's going to extend pre versus post COVID.
Yeah, it's very powerful.
Exciting.
Yeah.
I like the fact that there was already, you guys had.
So yeah, I mean.
3 years.
Sorry?
Oh, I just liked already how there's the span of 3 years, because a lot of fMRI studies are like 3 months, 6 months, and like it's not always enough time to really have pre and post effects.
Right.
Or like you can find a pre and post effect if you do it within a short enough time frame, but it's like, does that affect actually?
Yeah, it's a great effort by an amazing team.
Yeah. All right. So thank you very much for the presentation, and we'll move to the next speaker, but still.